Hello. Today we're going to be continuing our exploration of consumer resource models. Last time out, we learned about the Lotka-Volterra predator-prey model, and we learned about some of the issues that it has in terms of its dynamics around its non-trivial equilibrium, specifically the fact that it exhibits neutrally stable oscillations, which we'll talk about in a few minutes, which turn out to be problematic because they are structurally unstable. Today, we're going to be thinking about a more realistic predator-prey model and seeing what its dynamics are. So by the end of today, you should understand the idea of damped oscillations, which are in fact stable spirals or a stable focus, and learn how to construct a more realistic predator-prey model compared to the Lotka-Volterra model that we met previously. This is the model that we met last time, the Lotka-Volterra predator-prey model. We have a resource or prey by R, and a predator or a consumer given by C. We have a linear birth term for the prey, a linear death term for the predators, and then we have this type 1 functional response for our predator-prey interaction. Okay, so the last time we saw that if we analyze this model either geometrically or algebraically, we end up with a non-trivial equilibrium that is neutrally stable. In other words, it's a center. This happens when we have eigenvalues for a Jacobian that have zero real part and they're imaginary. So this means that if we start, say, here, we'll exhibit oscillations that look something like this. We're going around in this direction here. But the size and the amplitude of those oscillations depends on my initial conditions. So if I start over here instead, this time my oscillations will look something more like this. And likewise, if I start over here, it'll look like this. So while we stay on these orbits deterministically, if we begin on them, it's not a very good model because these oscillations are structurally unstable. In other words, a small change in our initial conditions leads to a different orbit. And that's problematic, especially because real systems are noisy. In reality, what we would expect to happen is something like this. Suppose we started here. We might start going down, but over time, maybe we go up and down, and we'll be wobbling around. And eventually what will happen over a long enough period of time, we'll hit one of these axes, and then one of the species will go extinct. So these oscillations, they're structurally unstable, and that means it's not really a very good biological model. So what we want to do is we want to try to adapt this model to make it a bit more realistic. Okay, so one way in which we can adapt this model, let's actually just go back up here a second, is we can think about this renewal rate or the birth rate for our prey population. And this time, let's think about what happens if we have a logistic renewal rate rather than an exponential. So let's write down our model. I'm going to change the time scale here just because I'm going to non-dimensionalize below. So dr dt here, so our equation for our prey is now going to be A times by R times by 1 minus R over K. So this is our logistic growth for our prey. Everything else is going to remain the same. We're still going to have a type 1 functional response for our predation term. And our consumer or our predator is telling us this efficiency parameter times by the functional response, and then it's the linear death rate. So now A is going to be our intrinsic growth rate. That will be positive, and K is our carrying capacity. Again, this is going to be positive. So we can show using suitable parameter substitution, as indicated below, that we can non-dimensionalize this model. I'll leave that as an exercise for you to have a bit of practice at that. We can write this model now as dx dt, change the time scale to little t now, where x is going to be the normalized density of our prey population. X times by 1 minus x minus alpha xy, and then our predator population dy dt is going to be equal to beta xy minus gamma y. So this is a little bit simpler compared to above. We only have 3 parameters now. Okay, so let's find the equilibria. Let's first find the null lines for our prey. So if dx dt is equal to 0, that implies that x times by 1 minus x minus alpha xy equals 0, which means that either x must equal 0 or 1 minus x minus alpha y must equal 0, which implies that x is equal to 1 minus alpha y, or equivalently, we can write this in terms of y, so 1 over alpha, that's by 1 minus x. Now, it doesn't matter whether we write these null lines in terms of x or y. Sometimes it's easier to write them in terms of y, or whatever happens to be on your vertical axis, because we usually write functions as y is equal to some function of x when we're sketching a curve in the xy plane. So often I'll try to write my null lines in this format here on the right-hand side, but sometimes for substitutions, this is a little bit easier. So it's good to know that we can switch them around. Okay, let's think about this first null line then. If x is equal to 0 and dy dt is equal to 0, so we're finding our equilibria that are along this null line here when x is equal to 0. Well, if we set dy dt is equal to 0, then we're going to have 0 is going to be beta xy minus gamma y, and we're told that x is equal to 0, so this first term is going to go to 0. So this is minus gamma y, which can only equal 0 when y is equal to 0. That's because we're told that gamma is a positive parameter, or at least we can deduce that gamma is a positive parameter from all of the other parameters that we had earlier. So if x is equal to 0, then y must equal 0. So 0, 0 is a trivial equilibrium. Now let's think about our other null lines. So if we're on this null line here, I'll indicate it in purple. On this null line, we're told that x is non-zero because we divided 3 by x. So let's think about dy dt. Well, dy dt being equal to 0, let's substitute in our value of x. We had beta xy, so we're going to have beta times by 1 minus alpha y and minus gamma y. Should be an extra y in there. So now, if we can either have, let's just do a little bit of rearranging here. I'm going to do y, I'm going to pull out y at that front, so we're going to have beta minus gamma minus alpha beta y. And that's going to equal 0. So this tells me that y must equal 0, or beta minus gamma minus alpha beta y must equal 0, which tells me that y must equal beta minus gamma over alpha beta. And this here is only realistic if beta is greater than gamma, which causes y to be positive. So here we saw that when we're on this purple null line here, when x is equal to 1 minus alpha y, either y is equal to 0 or y is equal to beta minus gamma over alpha beta. So we have 2 equilibria on this second null line. We now need to substitute this back into this equation here to find out what x is. So if y is equal to 0, then x must equal 1. Hopefully that should be pretty clear if we substitute this in green here. If we substitute this y is equal to 0 back into our equation for x, then x is going to equal to 1. And then if we think about what happens if we now substitute this value of y into here, do this on the slide below, So if y is equal to beta minus gamma over alpha beta, then x is equal to 1 minus alpha y, which is going to equal 1 minus alpha by beta minus gamma over alpha beta. Now these alphas are going to cancel. And we can write this all over one fraction. So we have beta minus gamma over beta. These betas are going to cancel. And sorry, there should have been a plus gamma, create a minus gamma. So we're just going to have gamma over beta. So we can bring all this together and summarize it. Our equilibria are going to be x star y star equals 0, 0, which is our trivial equilibrium. We had up here that if y is equal to 0, then x is equal to 1. 1, 0 is a semi-trivial or prey only. So the predator is extinct. We just have our prey. And then lastly, we had x is gamma over beta and y is beta minus gamma over alpha beta. This is our coexistence or non-trivial equilibrium. And this is only valid if beta is greater than gamma, otherwise it's biologically unrealistic. Okay, so let's think about sketching a phase plane for this now. In order to sketch the phase plane, we need a few things. We need to think about what are our null lines. We have our null lines above, so I won't repeat them again, but I will go back and highlight them. So we have null lines highlighted in yellow. We have a null line here at x is equal to 0. We have this null line, I'll do it in terms of y, just because the sketching will make it a little bit easier. Y is equal to 1 over alpha times by 1 minus x. This is going to be a straight line. We know that when x is 0, y is going to be 1 over alpha, so it's going to intersect the vertical axis at 1 over alpha. What else do we know? We have when y is equal to 0, then x is going to be equal to 1, so it's going to intersect the horizontal axis when x is equal to 1. We also have a null lines. Let's write down our null lines for dy dt. So just to make sure it's clear for our null lines for dy dt. Well, if we go all the way back up to our equations up here, for dy dt to equal 0, y must equal 0, or x must equal gamma over beta. Okay, so y is equal to 0, or x is equal to gamma over beta. So we have two more null lines here. And these are both straight lines. Y is equal to 0 is a horizontal null line along the x-axis, and x is equal to gamma over beta is a vertical line when x is equal to gamma over beta. Okay, so what I'll do to start with, I'll sketch the null lines whilst they're fresh in our mind, and then I'll think about the direction field. Okay, so I'll sketch my x null lines in green. So whenever we have a green line, that means that dx dt is equal to 0. So we had 1 when x is equal to 0, and 1 when y is equal to 1 over a times by 1 minus x. And then we have another null line at dy dt is equal to 0 when y is equal to 0, or as we've just found out on the right-hand side here, when x is equal to gamma over beta. Now, I'm drawing in this particular orientation here. I don't know that there is an intersection here between this, this point here. But we can show that this intersection exists if we have beta greater than gamma. Okay, so let's just draw on some labels here. I'll explain why in a second. So let's draw our values. This intersection here, this diagonal null line intersects the y-axis at 1 over a and the x-axis at 1. This vertical null line here intersects at gamma over beta. we have 3 equilibria, here, here, and here. And this point here we worked out was gamma over beta and beta minus gamma over alpha beta. Just check I've written that right. Yeah. Okay. So how do I know that we have this kind of intersection here and that this we don't in fact have this red line further over here, in which case there would be no intersection in the positive quadrant between the diagonal null line and the vertical null line. The reason being is that if beta is greater than gamma, then this value down here must be less than 1. If beta is greater than gamma, then gamma over beta is going to be less than 1. So that means that red null line exists between these 2 points here, between 0 and 1. And that means that this red vertical null line intersects our green diagonal null line. If beta is less than gamma, that means that this red null line is going to be on this right-hand side of that value 1. It's going to be greater than 1, and therefore there's no intersection between that red vertical null line and the diagonal green null line in the positive quadrant. So that's how I know, assuming you're sketching this for beta greater than gamma. So there's 2 versions of this phase plane. There's one where beta is greater than gamma and one where beta is less than gamma. Okay, so that's our null lines. I haven't labeled these yet, which I should do. So our red null line corresponds to dy dt is equal to 0, and the green is to dx dt is equal to 0. Okay, now let's think about my direction field. And as discussed previously, we only need to work out a direction field on 2 of our null lines, and then we can deduce the rest from there. So I'm going to focus on the axes because they're nice and simple. So let's think about on the null line x is equal to 0. By definition, dx dt is equal to 0, so we must only be moving left or right. What about our value for dy dt of this null line? Dy dt is going to equal minus gamma y. Go back up here and check y. If x is equal to 0, then this is going to be equal to 0. So we just end up with minus gamma y. And this is always going to be negative for positive y. So that means that this green null line here, our arrows must point down because dy dt is always negative whenever we're on that null line. Okay, let's think about the red horizontal null line now. So this is y is equal to 0. By definition, dy dt is equal to 0. Dx dt is now going to be x times by 1 minus x. We had previously a minus alpha xy. So this here should be minus alpha, not a minus a. The dx dt equation, let's just go back up here. This is our dx dt equation. We get a minus alpha xy. Y is equal to 0, so we just have x times by 1 minus x. We see here that this is going to be greater than 0 if x is between 0 and 1. It's going to be less than 0 if x is greater than 1. So that means when we're between 0 and 1, our arrows on this null line will be moving to the right. And when we're greater than 1, they'll be moving to the left. Okay, so we can deduce everything else from here. In this region here, I must be moving down and to the right because I've not crossed any null lines. So we must be moving in the same direction. I can't be moving up because I'm only a little bit off this axis and I haven't crossed a null line, so I can't change the direction of that null line. So I have to be moving down and to the left, down and to the right, sorry, in this region here. And if I now cross, if I now move along towards this bottom axis to the right, these arrows here are passing to the right. And that dy dt null line, that vertical one, dy dt is equal to 0, so I can't be moving up or down. When I pass through that null line, I must be moving to the right. Okay, now that I've crossed through that null line, though, on this side of the null line, we have dy dt being negative, we're moving down. On that null line, dy dt is equal to 0. On the right-hand side of that null line, dy dt must be positive. So in this little quadrant here, we must be moving up and to the right. So in this little triangle down here, we're moving up and to the right because we've passed through that null line where dy dt was equal to 0. So on the left-hand side of that vertical red line, dy dt is negative. On the right-hand side of it, dy dt must be positive. So I'm moving up and to the right now. That means that this green null line here, dx dt is equal to 0 by definition, so I can't be moving left or right. I have to be moving up or down. I've just found out I'm moving up in this little triangle down on the bottom right, so I must be moving up here as well. Okay, now if I move over to this region here, just been told that we're moving up in this region, and we passed through a green null line where dx dt was equal to 0. So in this bottom triangle here, dx dt was positive. On the green line, dx dt is equal to 0. So above this green line, dx dt must be negative. Okay, so we've passed through 0. That means we're moving to the left in this region here. So moving up and to the left in that top right region. Again, if I now start moving in this direction, as I pass through this red null line, I have to be moving to the left because I've not changed through a green null line yet. And then I'm now transitioning into this top left region here. In that region, I have to be moving left and down. So I'm moving left and down in this region. Why is that? Well, on this side here, dy dt was positive, I was moving up. Here, dy dt is going to be equal to 0, so I'm not moving up or down. And then here, dy dt has to be negative. So pass through 0. So we see we've managed to fill in all of the directions just by working out what the direction was on these two null lines here. So the last thing to do is to think about a possible trajectory. Well, let's suppose we start over here, moving up and to the left. It's possible that I could move up and to the left like this and just go straight into that equilibrium. But let's suppose I move something a bit more like this, a bit slower, moving up and to the left. As I cross this null line, I have to be moving exactly left, not up or down at all. I'm now moving down and to the left. I realize I've missed an arrow off here. So now moving down to the left. Down to the left still. So moving down to the left. When I cross that green null line, I'm moving down. Again, I could be just going straight in like this. Or perhaps now moving down and to the right, I might cross this null line at the bottom. Again, I have to cross that null line in the direction which my arrow is crossing, which is horizontally to the right. And then perhaps I continue this kind of pattern. So maybe I've got a stable spiral or a node. In order to figure that out, I have to do a little bit more digging in terms of our looking at our Jacobian at that coexistence equilibrium. So that's what we're going to do now. Okay, so let's find the stability of the coexistence equilibrium. First thing we need to do is find our Jacobian. So this is going to be 1 minus 2x star minus alpha y star minus alpha x star beta y star beta x star minus gamma. I've gone through that quite quickly there. That I'll leave as an exercise for you to check that that Jacobian is correct from these equations up here. Remember, we're taking our partial derivatives with respect to x and y and putting them in this Jacobian matrix. So what do we need to do? We need to look at our coexistence equilibrium x star y star is equal to gamma over beta, beta minus gamma, alpha beta. So we need to substitute these values into the Jacobian above. So our Jacobian is going to equal 1 minus 2 x star is going to be gamma over beta minus alpha y star. So the alphas are going to cancel. We're going to have beta minus gamma over beta. In the top right, we'll have minus alpha gamma over beta. Bottom left, we'll have beta minus gamma over alpha. And then in the bottom right, x star is gamma over beta, so we'll actually end up with a 0 here. Okay, so we can do a little bit of simplification here. Let's just think about this term up here. So we can write 1 minus 2 gamma over beta minus beta minus gamma over beta. We can simplify this. So I'll just indicate this yellow highlighted region is the one that's from our Jacobian. We can simplify this into one fraction. We'll have beta minus 2 gamma to minus 2 gamma minus beta plus gamma all over beta. These betas will cancel. We'll have a plus gamma and a minus 2 gamma, so we'll end up with just minus gamma over beta. So that means we can write our Jacobian as minus gamma over beta minus alpha gamma over beta, beta minus gamma over alpha, and 0. Okay, so at this point, we can't just read off our eigenvalues. We can either look at our trace and our determinant to work out the sign of our eigenvalues, whether they're real or complex, or we can just calculate them using the characteristic equation. I will work out the trace and the determinant here, because it's a little bit easier. That's called power trace. This is going to be just minus gamma over beta. Gamma and beta are both positive constants, so our trace is always negative. And the determinant is a little bit more complicated. The terms on the main diagonal will cancel, and then we're going to have a minus alpha gamma over beta, so we'll just have a alpha gamma over beta times by beta minus gamma over alpha. So these alphas are going to cancel. We can write this as gamma, beta minus gamma over beta. And if we go all the way back up here, this coexistence equilibrium, which is the point we're looking at, is only valid if beta is greater than gamma. So that means that we're looking at the stability of the coexistence equilibrium, so we're assuming it exists in the first place. So if it only exists if beta is greater than gamma, so for it, whenever it exists, this term here has to be positive. So we can say that whenever the coexistence equilibrium exists, we have a negative trace and a positive determinant. Okay, and this is since beta has to be greater than gamma for our coexistence equilibrium to exist, or more correctly, for it to be biologically realistic. So we have either a stable node or a stable spiral. Whether we have a node or a spiral depends on whether we have real or complex eigenvalues. So we need to look at the sign of our trace squared minus 4 times our determinant, and that will tell us whether we have real or complex eigenvalues. So when is this positive? I'm choosing positive as an arbitrary choice. I could have chosen negative, but here this will tell us when we have real eigenvalues. So if we square our trace, we're going to have gamma squared over beta squared. And then if we subtract 4 times our determinant, 4 gamma beta minus gamma over beta. And this has to be greater than 0 for us to have real eigenvalues. So all I've done there is I've taken my trace and determinant from the slide before. I've taken the trace squared minus 4 times the determinant. I'm seeing when this is positive. Okay, so we need to do a bit of manipulation here. I can multiply throughout by beta squared because beta is positive, and that doesn't change the sign of the inequality. And I can also divide through by gamma for the same reason. So we're going to have gamma minus 4 beta. That's by beta minus gamma. We need this to be positive. I can expand out that bracket to get gamma minus 4 beta squared plus 4 beta gamma. And I can take that 4 beta squared over to the other side. So we're going to have gamma plus 4 beta gamma got to be greater than 4 beta squared. And then I can divide both sides by 1 plus 4 beta. And we'll get gamma has to be greater than 4 beta squared over 1 plus 4 beta for our eigenvalues to be real. So if gamma is greater than 4 beta squared over 1 plus 4 beta, then our eigenvalues are real. So we have a stable node. And if gamma is less than 4 beta squared over 1 plus 4 beta, then our eigenvalues are complex, and we have a stable spiral. In other words, we have damped oscillations. So how can we interpret the dynamics of this system biologically? Well, in the long term, our predator and prey populations are going to tend towards a stable coexistence equilibrium. And that's regardless of whether we have real or complex eigenvalues. We can see this from the phase plane up here, that as long as it exists, we're going to tend towards that equilibrium in the middle. So in the long term, whenever we think long term, think about it as something stable or unstable. It's stable, so we know that in the long term, these populations are going to tend towards those particular population densities, gamma over beta and beta minus gamma over alpha beta. But let's have a think about what these gammas and betas mean. If we go back up to our original equations, non-dimensionalized equations here, gamma was our death rate for our predators, and beta was our functional response, or rather our attack rate for our predators as part of that functional response, scaled also by its efficiency. So what this is then saying down here, if our mortality rate for our predator is sufficiently low, in other words, if it's below this threshold here, 4 beta squared over 1 plus 4 beta, then the populations will approach the equilibrium through damped oscillations. So with a sufficiently low death rate for the predator, we're going to get damped oscillations and also have this stable spiral into the center. And if we have a sufficiently high death rate, so if gamma is above this threshold here, gamma is greater than 4 beta squared over 1 plus 4 beta, then we'll have a stable node, and therefore we won't oscillate all the way into that long-term equilibrium. So if we think about short-term and long-term dynamics, in long-term we have a stable equilibrium, everything tends there. In the short term, depending on whether gamma is sufficiently high or sufficiently low, we will have the population spiraling in if the predator's death rate is sufficiently low. And if the predator's death rate is sufficiently high, then we'll just approach it monotonically. So this is a more realistic model than our lynx hair model that we had previously in the just standard Lotka-Volterra model, where we had these neutrally stable cycles. Here we have cycles can exist but they're damped oscillations. So in some ways, it's more realistic in the sense that we have oscillations that are not structurally unstable, but this model doesn't cycle indefinitely like we see in the lynx hair population. So that suggests that we maybe need to make some more tweaks to this model to properly fit that lynx hair dynamic. Okay, that's it for today. There's a self-study problem here in non-dimensionalization of the model before.